Hello, students. Here we're looking at another application of derivatives, and that's dealing with rates that are related. An example of this would be thinking about, I don't know, let's say we have a balloon that we're inflating, and we can look at, for example, the rate of the radius going up as compared to the rate of the volume as it goes up, as compared to the rate of the surface area as it goes up. And dealing with these related rates is one of the ways that we use calculus a lot. All right, so we're going to start off by talking about, I guess this is really an optimization thing. So which point on the graph of y equals the square root of x is closest to the point 5, 0? I'm just going to kind of sketch this to see what's going on. 1, 2, 3, 4, 5. And for the graph of square root of x, we've got 0, 0, 1, 1, 4, 2. 5 doesn't have a nice clean number, but it's going to look something like this. All right. The points here, and I'm just going to use some kind of arbitrary point that I think will be pretty close. I'm going to call this x comma the square root of x. And our goal is to figure out the distance between that and the point 5, 0. I'm going to use the Pythagorean Theorem, which tells us that the distance is equal to the square root of each of these. I just made an erase. I didn't mean to make that erase. Each of the legs of this triangle. So we're really talking about 5 minus x, that's the x distances, squared, plus 0 minus the square root of x squared. Pythagorean theorem, a squared plus b squared is equal to c squared, and I just took the square root. Cool. This is an equation for the distance, so let's take the derivative of this. I'm going to call that d prime, and that's going to be 1/2 because this is a 1/2 exponent. I've also learned that makes that a negative 1/2, so we end up with stuff on the bottom. 5 minus x squared, and then plus that squared is going to be just x. All right. Since we have stuff on the inside, I also have to apply the chain rule. 5 minus x squared is going to be 2 times 5 minus x to the first times negative 1 for the chain rule. And then that's plus x, so we've got plus 1. Okay, we know for max and min stuff, I've got to use some critical values. So if we're dealing with when this is equal to 0, we're talking about the top of this, so 2 times, that's supposed to be a 5, and I wrote a 2 instead. 2 times 5 minus x times negative 1, and then plus 1. I like it. I'm going to move the 1 to the other side, so we get negative 1. And then on this side, we've got negative 10. And then plus 2x. That's going to give us 9 is equal to 2x, and x equals 9 over 2. Okay, that looks like a pretty good guess for this point. One of the things that I could do to see what's going on here is to use that x value in the derivative and see what's going on, or take the second derivative, do the second derivative test. I also do want to check the bottom, so things that are undefined, and that would be essentially saying that 5 minus x quantity squared plus x is equal to 0. I'm going to distribute that out. 25 minus 10x plus x squared plus x is equal to 0. So x squared minus 9x plus 25 is equal to 0. That is totally not factorable. And if I think about this in terms of doing some kind of completing square quadratic formula, we'd have a b squared minus 4ac of 81 minus 100, which is going to be imaginary. So we don't have to worry about that at all. Woohoo! Okay, so since we don't have to worry about that, I want to double check that this point is usable. So I'm going to find d prime of something that is less than this. I'm going to go with 0 because it's easy. And then do the same thing for something that's bigger than that. I'm going to go with 5 because I think that'll be pretty easy for us as well. So d prime of 0, plugging that in there, I'm going to end up with, I'm going to change color so I don't run into stuff, 1 over 2 square roots of 25. And then for the second part, I'm going to multiply by this. That's going to be 2 times 5 times negative 1, which is going to be negative 10 plus 1 is negative 9. What I really care about is that this value is less than 0. So we're talking about d prime of 0 being less than 0, d prime of 9 over 2 equaling 0, and now we're going to try 5 to see what happens. So again, for the first part, I just turned on the eraser. We're going to end up with 1 over 2 times the square root. When I plug 5 in, I'm going to get 0 and then plus 5. That's a positive number. And then for the other part, we're going to end up with 0 for the first part, and then plus 1, which is a positive number as well. So we've got d of 5 is going to be greater than 0. Graphically, what this means is that at 9 over 2, we have a horizontal tangent line. Before 9 over 2, we are decreasing. And after 9 over 2, we are increasing. So if we're trying to find the closest point, that's the minimum distance, that's going to be the point where x is equal to 9 over 2. Plugging that into our equation, the y would be the square root of 9 over 2. The second thing that I want to remind us of is implicit differentiation. We use this to take the derivative of things that are using different variables. So for example, if I wanted to take the derivative with respect to time of something like x squared plus y squared, because we're using a different variable, we have to include the derivative of the function itself within that. So this would be something like 2x for the derivative of x squared multiplied by the derivative of x with respect to t, which we could call x prime. Today I'm going to use dx dt to make the most of that. And then same thing for the y. We've got 2y, and then I'm going to say dy dt. I could also say y prime if I'd like. All right, so now we're getting into this problem. I'm going to do some annotation on what's going on here and then use that to kind of build an answer for us. So how fast is the area of a square increasing? So we're talking about dA dt. That's the area of a square increasing. That's how I'd write that. That's the rate of area divided by the rate of time. I also know that a is equal to s squared, so that might be important in a minute. At the instant when the sides are 4 feet long. So at some point, we're talking about sides equaling 4 feet. But since they're changing, any of the calculus I do, I need to do before I plug that number in. Because if I take the derivative of something that has s equals 4, we know the derivative of a constant is 0. All right, and the third piece, sides increase at a rate of 1.5 feet per minute. So sides increase, that's the change in side over the change in time, ds dt, is 1.5. I'm looking for dA dt. The good news is that I have an equation that involves a. So if I wanted to take the derivative of a with respect to t, that would be dA dt. The derivative of side squared with respect to t would be 2s, and because it's implicit, I have to do ds dt. In other words, because we're using a different variable, I have to use that implicit method. Now that we have this stuff, we can use the numbers that we have here. So dA dt is equal to 2s, and s is 4, so that's going to be 8. ds dt is going to be 1.5, so that's going to be 12. And for area, that would have to be feet squared per second. Cool, we've got one that just has some variables there. So we're given x equals 1, y equals 3, and again, we're not going to plug those in until later. X is decreasing at 2 units per second. Okay, I'm going to call that dx dt. And I'm also going to write that down below. So dx dt is equal to, decreasing, -2. I'm going to add x equals 1 up above that. Y is increasing at 2 units per second. Cool. So that's dy dt, and that's +2. I'm also going to say y equals 3. How fast is z changing at this instant? So I'm looking for dz dt, and we've got to figure out if that's increasing or decreasing. The other thing that might be helpful is I don't know z for this. I know x and y, so I can use that equation to plug that in, and using 1 and 3 to figure out z, I get that z is equal to 81. Okay, so now I'm going to go with my equation. Z is equal to y to the 4th, x to the 3rd. I'm going to take the derivative of both sides with respect to time. So we get dz dt, that's what we're looking for. And here I've got a product rule. So that's going to be 4y to the 3rd times dy dt, x to the 3rd, plus 3x to the 4th, and by the 4th I mean second. That's going to be dx dt, and then y to the 4th. Now we're going to plug stuff in and see if this works. So we got dz dt, we don't know what that is yet. 4y is 3 cubed, dy dt is 2, x cubed is 1, plus 3, x squared is 1, dx dt is -2, y to the 4th is 81. We've got numbers for everything but dz dt, so we are in good shape. I'm just going to do some simplifying. We're going to have 4 times 27 is going to be 54, and then 108 times 2 is 216. I'm sure if I messed that up, you'll let me know. Then we got -162 times 3 is going to be -586. When I do some magical subtraction thing, I'm going to end up with -370. And z is going to be a linear unit, so that's going to be units per second. And because it's negative, z is going to be decreasing at that point. All right. Oil spills in a circular pattern. I don't know what type of thing I'm looking for yet. Radius increases at a rate. Okay, so that's changing color. dr dt of 50, I think that's feet per minute. Yep. So I'm going to say dr dt is equal to 50 feet per minute. How fast are both the circumference and area? Ooh, two different things. So that's dc dt and dA dt. We don't know what either of those are. When the radius is, and we're giving two different values for the radius. So I'm going to do this problem twice. Once we get to the end, we got r equals 20 and r equals 50. Cool. I'm going to go with circumference first, just because that's a little bit of an easier formula for us. So dc dt is equal to 2 pi times 1 times the r dt. And when I plug those numbers in, we've got two different values. We're going to have 40 pi, and that's going to be a linear unit, so that's feet per minute at r equals 20, and 100 pi feet per minute when we're at r equals 50. Cool. For the area, we're looking at a is equal to pi r squared, so we got a little bit more work. We're going to have dA dt is equal to 2 pi r, hey, that's the circumference formula, times dr dt. I'm also realizing that I totally just misread my own work and that those answers are totally wrong. So I apologize, because we're not plugging in the r values, we're plugging in dr dt. I was wondering why we got different values for that. It's weird. That's what happens if I don't pay attention to what I'm doing. So if I'm plugging in dr dt here, we get 100 feet per minute. Sorry, 100 pi feet per minute. Now, dealing with dA dt, we have to plug in those separately. So we're going to have dA dt at r equals 20 is equal to 2 pi times r, which is going to be 40 pi times 50 feet squared per minute. That's going to come out to be 2,000 pi feet per minute. And then for 50 feet, so dA dt at r equals 50 is going to be 100 pi, and then I'm going to plug in my 50 feet per minute, so 50 feet squared per minute is my final units. That's going to be 5,000 pi feet squared per minute for the area of that. All right. A general strategy for those of you that have or are currently taking physics, this strategy reminds me a lot of solving mechanics problems in physics. I'd say first, identify everything. So find the rates, find the values that you need, and just write all that stuff down. Don't plug in anything, just find all of this stuff. Once you've done that, we're going to have some kind of formula, or you'll be given some kind of equation. We're probably going to need to take some derivatives, and by probably I mean you will. And just as a reminder, these are all going to be implicitly, there we go, because we need to deal with different variables. Then we're going to plug stuff in and solve for any missing pieces. The last piece that's really important, I want you to be able to interpret your answer, and that includes units too. So looking at this example, and it's worth probably pausing here before going through the video. Try this on your own and then come back to this. So we're resting in a birdhouse 24 feet off the ground. I'm going to say h equals 24. Using a 26-foot ladder. Oh man, that he leaned against the pole. So here's the birdhouse. here's my ladder. Starts pulling the base of the ladder away. So as the ladder gets pulled away, this 24 number is going to start to slide down. So it's pulling the ladder away. I'm going to say this is x, so dx dt is going to be 2 feet per second. We actually don't need that initial height because we only care about this when h equals 10, and we're looking for the change in height of the ladder. Okay, so I'm going to get rid of that for a second. I don't know why I crossed it out when I can use my magical eraser. Let's think about ways that we can connect to these two. The way that I'm thinking right now is that we can use Pythagorean Theorem, and in doing that, we can say something like x squared plus y squared is equal to 26 squared. When I take my derivative, I'm going to have 2x dx dt plus 2y, I don't know why I started to make a fraction, dy dt is equal to 0. All right, I want to get dy dt, which I call dh dt over there by itself, because that's what we're looking for. I know that my y value is going to be 10, so this is going to be 20 dy dt. I know my dx dt is going to be 2 because it's increasing. I don't know what x is right now, so I'm going to hold off on that for a second. And because of that, I can't really solve this equation yet. So I've got to figure out what x is when y is 10. For that, I'm just going to use the Pythagorean theorem that we're given. We've got x squared plus 10 squared is equal to 26 squared. This is going to be x is equal to 16. Because this looks like a 5, 8, 13. That's not a thing. 5, 12, 13. So x should be 24. All right, you can check my math, but that should be the right answer for that. So now when I plug this back in, we get 4896 is equal to negative 20 dy dt. Dividing by negative 20, we get dy dt is equal to 96 over 20 on the negative side. And that would be feet per second. We have to understand that this means that the ladder is falling down the wall when the height is 10 at a rate of negative 96 over 20 feet per second. There's some more related rate problems at the link supplied here. Definitely worth spending some time on, but in the scheme of calculus, we're really only looking at like a small part of the whole shebang here.